Good evening. It is the 28th of March, 2022. This is the Randomizer. I'm Charles Schultz, and we have a fascinating show tonight on a simple physics term that applies all across the field, precession. So precession is an interesting subject because we often think of gyroscopes and spinning objects, and precession is one of those properties that they exhibit where the axis tumbles around in some predictable manner. And we're going to talk about how that happens and why and some of the effects. We're going to go from the nanoscale to the micro to the macro, and we're going to talk about those effects a little tonight. I'd like to encourage everybody to go to schultzlaboratories.com or universeciencecenter.com, sign up and become a member, support our growth, the addition of our galleries and more interactive exhibits in 3D. It's a lot of fun, and bring some kids with you, let them see it. They'll know exactly how to get in there and do things. It's one of those things where the kids know exactly how it works and a lot of us adults don't, but that's okay. It's all about learning and teaching, and the more fun it is, the more they'll hang in there. If you are an educator with a specialty or a trade or a subject that you're very good at and you wish to share your knowledge, contact us and let us set you up with a virtual classroom or gallery to exhibit your works and to share your skills and to teach others. It'll be a great deal of fun, and it's one of the best things we can do. The world needs more education. So, that being said, the Randomizer happens 6 p.m. Eastern Standard Time every weekday, and we're going to have the random technical term chosen every day and discuss it and get into some of the details. And we hope that you'll come in with your live questions, ideas, and comments and share them with us during the show. Also, our lessons on robotics will be starting very soon on Mondays at 9 p.m. Eastern Standard Time. So there will be a schedule posted, and it'll be a lot of fun. We're going to use some interesting examples. You'll be able to follow along. And if you want to build your own robot, we'll show you exactly how to do it. The hardware, the power, the programming, the sensors, the whole thing. So let's get started with our episode of the Randomizer for Precession for tonight. So what is precession? Everybody knows basically that if you spin a top, and a lot of us had kids' toys, tops or gyroscopes, and you would generally stand them up, pull a string, and they would spin. And we'd notice in a little while they wouldn't stay vertical, but they would begin to wobble slowly in their movement. And the wobble would depend on the direction that you spun it. Now there's a very simple rule, and it's called the gyroscope rule. And if you take your open hand and you clench it with the thumb sticking up, this is the axis around which the spin will occur, like the North Pole. Shoot your finger forward like that. That's the direction you want to push the spinning gyroscope. It's spinning in the direction that your fingers curl. Do this. When you push the pole forward, the gyroscope will tip in the direction of this finger. And so this precession happens because when a force applied at right angles to the gyroscope tries to move it and it's spinning, conservation of momentum makes it move 90 degrees to that force. If you have a gyroscope spinning clockwise, it does exactly the same. If you push it, it'll tip to the right. Now, this principle holds for any spinning object. And if you hang a gyroscope on a string, you will notice that it moves around and around in a circle around the string as it's spinning. It is precessing at right angles to the force being applied to its axis. This interesting thing is that if you know anything about magnetic fields and electronics, you know that there's a magnetic field solenoid law that works almost exactly the same. And it raises some very interesting questions. It implies one of a couple of possibilities. One, that something about the orientation of the electromagnetic force is identical to the gyroscope rule. We're probably right there. Another is that maybe for the four-dimensional space-time that we inhabit, not counting the forces, that there's only a certain number of restricted ways that things can move, and therefore gyroscopes and electromagnetic fields are kind of constrained by degrees of freedom and must move in these directions. That's a possibility too. Another is maybe it's a mixture of both. And the final possibility that I can think of is maybe we're entirely out to lunch and none of us connected at all. So there's four logical states that come from that thinking. However, We do know that the laws work, and it takes some pretty sophisticated mathematics to understand why. For the most of us who are not physicists or mathematicians, we simply observe it and we know that it's a fact, that this is the way the system works. And for many instances, that's perfectly fine. It allows you to understand to some degree what's happening. So now let's look at how this effect stretches down to the smallest scale of matter. It turns out that particles often have a charge, and therefore, as they have a spin, they have what's known as a magnetic moment, that they have an axis of magnetic alignment. If you take a particle such as a proton, and it's in a nucleus of an atom, and you apply an external magnetic field to it, a strong magnetic field lined up with the particle will make its axis precess around the magnetic field. So the particle is spinning with its north lined up with the magnetic field because it has charges moving in them and therefore a magnetic field of its own. So the particle will dance around a magnetic field, and a radio frequency will make it do it as well. It will ring at a certain frequency of radio waves. This is called the Larmor precession, and particles are often constrained in a magnetic field, and they ring with a certain magnetic frequency, a radio frequency we can detect. And this is the fundamental basis of nuclear magnetic resonance, or NMR. And what do we use that for? Medical diagnostic imaging. NMR is the basis for magnetic resonance imaging. So when you go to the doctor and they place you in the cavity of the machine, they're applying an incredibly powerful magnetic alignment that makes all the particles' nuclei line their poles up with it. Now, it only works with certain atoms and only with specific radio frequencies, but this allows you to image specifically hydrogen atoms or specific other atoms and get a picture of what's going on in the body. And so you can get extremely detailed images of the interior of the body without having to slice anything open or put cameras anywhere. That's one of the basic effects of precession. The nuclei, the particles in the atoms themselves, are precessing like gyroscopes under these conditions. Powerful magnetic field, radio waves. Okay. And of course, we've all seen gyroscope toys themselves, and we see often enough astronauts in the space station playing with gyros or spinning objects, and we'll find that they do some strange or somewhat anomalous things to our perception. But it's all well within the rules. But here we get into something on the macro scale. Our planet itself is a giant gyroscope. It spins on its axis. And if you were to stand out in space and look at the planet, our planet is spinning counterclockwise around the North Pole. So the west half of the planet is traveling toward the east. Now, if you're standing on the surface, what you see is the sun rising in the east and moving to the west. The reality is the sun is basically stationary, we're moving against it. But as the planet is spinning, something very interesting happens. The planet, like a gyroscope or a top spinning down, has a pole that precesses. The north pole of the planet moves around. Now, if you go outside at night and you look at true north in the sky, you'll see a star called Polaris, which is the North Star, and it's a little less than 1 degree aligned with the north pole of the Earth. Now, our planet's pole is wobbling slowly, it's precessing. And the first form of precession is just a wobble, and it takes roughly 26,000 years. This is actually a period of 25,771 and a half years as this precession occurs. And the effect is, in the year 14,000, our North Pole will not be at the North Star Polaris, it'll be pointing to the star Vega, the blue-white star. And so that will be our new North Star in 12,000 more years. If you hang around, let me know how that looks. So that's our first form of precession. And why is this an important thing? Our climate changes regularly in different manners. And a large contributor to that effect is biology and the life forms on the Earth and the amount of sunlight striking the ground. But what we're going to focus on right now is something called Milankovitch cycles. There are 4 specific types of variation in the spin of the Earth. And the first one I just mentioned, the wobble of the pole. This is the 25,771 and a half year cycle that I just mentioned. And this is a very powerful influencer of what I would say is when spring comes in its orbit around the planet. And the reason for it is very simple. Our planet is not uniform inside like a billiard ball. It has two major differences that make it somewhat lopsided. In the very early history of our planet, it's pretty clear that another smaller planet collided with the Earth, and its core merged with our core, but not perfectly. The two cores, one smaller and the one larger one that we started with, are slightly off center. And so our planet has a mass concentration that's not dead center. And this lopsidedness actually influences the orbits of satellites around the Earth. But it also does another thing. It creates a lobe, almost like the pole of a magnet, but it isn't, it's mass. And that is influenced by the pull of the sun and the pull of the moon. The other effect is this: because the Earth does spin, the equator slings out slightly. The bulge around the equator is a little bit higher than perfectly circular, and the poles are shorter, a little bit shorter than you would expect. So this equatorial bulge is the other handle that the Earth has that the sun and the moon can pull on, as well as other planets such as Jupiter. So this pull varies some of the tipping of our Earth constantly. It influences it a little bit, and it takes many thousands of years. So the first one of these influences, of course, the wobble that I talked about, that almost 26,000 year cycle. The second one is that the obliquity or the tilt of the planet changes. So you know that the gyroscope can be pointing straight up and down, or it can be at some angle as it's spinning. Well, the obliquity or tilt changes in a period of roughly 41,000 years. We don't have an exact number for that. And it changes from 22.1 degrees to 24.5 degrees. Right now we're at 23.4. We're right in the middle of the two pretty much. And so it tips down and then it straightens up a little, and then it tips down and straightens up a little. So this is happening at the same time that the pole is wandering around or precessing. So that's the second of the Milankovitch cycles that changes something about our climate. And the reason that's important is if the planet is vertical, the seasons are milder, but snow can build up on the poles, and then the planet can get into an ice age. When the pole is tipped down, the seasons are more variable, and there's less opportunity for ice and snow to build up at the poles. And this means that even though the climate has broader changes from season to season, it prevents the planet from going into an ice age. So the more vertical our pole is, the more likely we are to enter an ice age, and the more tipped we are, the less likely. Now, one of the things that keeps us from tipping any further is the moon acts as a ballast. It tries to right our planet all the time, and that equatorial bulge is influenced by the moon and the sun to try and stay upright. Mars, we know, has no large moon, and it has a very a wide range of tilts, and as a result has extremely different climate from time to time. Our moon stabilizes our climate for us. All right, so the third type of wobble that we have is called eccentricity. And this is how circular our orbit is, whether it's an ellipse or a more nearly uniform circle. And over the course of about 100,000 years, the eccentricity of our orbit changes. So right now, we're in a pretty circular state. It goes from 0.0034, which is a nearly perfect circle, to 0.058 over this period of about 100,000 years overall. So it wobbles out long and then goes back to more circular. So this change of the orbital shape means we get more variation in seasons from winter to summer. And it's because we can have a difference of like 5 million kilometers of our distance from the sun to the Earth, or 3 million miles roughly. Finally, the fourth type of wobble we have is called apsidal precession. And what this is, the plane of the ecliptic, this is where the equator of the sun is projected out like a sheet of paper all the way out into space. The plane of the ecliptic is where the orbits of planets are generally aligned. All the orbits can tip a little above and a little below that plane slowly. And our orbit has an apsidal precession that changes flatter or a little wilder or a little flatter back and forth over a period of about 112,000 years. So when you add all of these cycles up, we find that Milankovitch, who was very interested in changes in our climate, was dead right. He was absolutely on the numbers, and the changes of ice ages and glacial periods matched for roughly 480,000 years, all the way back, where all of these cycles lined up just like they did. And our last ice age was 11,700 years ago, roughly. And people feel we're due to start entering a new one soon. Overall, when you put all of these cycles together, we have a roughly 23,000 year cycle from all of these harmonics adding up. All the cycles don't add up absolutely equally. They produce some chaotic effect sometimes. And we've been very fortunate to be in a very clement period of time for the last few thousand years, something that humanity has not experienced before. So one of the things that allowed us to reach technical maturity or growth was the fact that the climate's wild cycles came to an end, and now we've been in a very peaceful period. So we've had about 7,000 years of pretty peaceful climate. That is due to end. But the other thing is these cycles are adding up in a different way now, and that cycle is going to stretch out. So we don't know exactly what's going to happen because there are contributions not just by the tilt of the axis and the size and shape of our orbit, but also by biology itself. Organisms can make the ground lighter or darker. They can also absorb or emit more or less methane or carbon dioxide. So the plant life and the bacterial life in our environment have a huge effect on how our climate changes and what those cycles look like. If you go back to a period of about 600 million years ago, our planet was in a stage called snowball Earth. And it was only methane generating bacteria near the equator that lived in the oceans that apparently started metabolizing enough and creating enough methane that it raised the global temperatures, and a huge burst of oxygen occurred, and then the complex life that we see today came to be. And that was at the very beginning of the Cambrian period. So this is something that changed the face of our planet and of the development of life and how it proceeded. So life supports life, and it does so by altering the environment in these ways. And it's recorded in many ways. We can see these changes in the geology of the rocks of our planet. And part of those cycles are changed by how far the moon is from the Earth and how quickly it goes around the Earth. Right now, the moon goes around the Earth roughly once a month, a little more than 28 days. And so our cycles are based on that lunar orbital cycle. Now, somebody once said, without tides, life on Earth just wouldn't have developed, and they had some great kind of an explanation for it. And the one thing they've said was, so if we didn't have the moon, our planet probably wouldn't have life. And I take exception to that for the following reason. Without the moon, we still would have tides, driven by the sun. The only difference is our tides would always be high tide at noon and midnight, and low tide at 6 a.m. and 6 p.m. And that would be the only difference. The tides would be about half as intense. So the moon donates a huge amount of variation to our tidal cycle, and it also drives where the tides are by its position. The sun also contributes. Sometimes the two line up, and you get spring tides. When the moon is at full or new phase, your tides are highest. When the moon is at right angles, so it's half phase, gibbous, waxing, or waning, then it's pulling its weight, and the sun is pulling against it, and you get spring neap tides, very weak tides. And so the tidal tables take into account the shift of the moon and the sun simultaneously. And that's why they make tidal tables. It's a little more complicated than you think. So anyway, precession. It is the results of a spinning system to a disturbance, and it causes it to wobble. Our planet does that as well, and it's a major contributor to climatic shifts over the millennia. So I hope that this has been, an explanation that makes sense. And the floor is open for questions if anybody has them. And meanwhile, I'm going to encourage you to go to schultzlaboratories.com or universeciencecenter.com. As I said, sign up for our classes, sign up as a member, help us develop and grow. and it's going to be well worth it. When you see what we've got, I think you'll be impressed and you'll want to join us. And again, if you're a teacher or an educator and you want to share your expertise, contact us. We'll help you do that in your own virtual studio or classroom. So, finally, my quote for the day, sorry about that. For the eyes of the Lord are on the righteous, but his ears are open to their prayers. But the face of the Lord is against those who do evil. And this is 1 Peter 3:12. And this is simple. Just do the right thing. That's basically what it's telling you. You'll find favor if you do the right thing. Well, I hope that everybody has enjoyed this presentation. Join us tomorrow at 6 p.m. for the randomizer, and we'll have a new technical term we pull out of our digital hat, and we'll talk about something else fascinating. And if you've learned something, let us know. Give us some feedback. Contact us. Please join us and talk to us. I think it'll be something that you won't forget. So, everybody have a wonderful evening, and I'm glad you came. I'm Charles Schultz with Schultz Laboratories and the Randomizer, and I hope that you have a wonderful evening and make the world a better place. Thank you for being here today.